Hello everyone. Today we are going to talk about deletion operation in binary search tree. So whenever we have to delete a node from a binary search tree, we have to first search for that node. If the search is successful, that means the node is present in the binary search tree, then only we can remove, otherwise we cannot remove a node. So if a node is found, then we have to execute the deletion algorithm. The deletion algorithm in binary search tree basically has three cases. First one is we are trying to delete a node with no children. That means we are trying to delete a leaf node. Second case is we are trying to delete a node with one child. That means either the left child or the right child is present. And third one is we are trying to delete a node with two children. So we will quickly look at the examples corresponding to all the three cases. So here we are trying to delete a node that is -4. And we can see -4 is a leaf node. So in order to delete this node, what we have to do? We have to simply put left of this node 2 to null. That means we have deleted the node, and after putting this left of 2 to null, we have to release the memory occupied by -4 node. So after the removal, the structure of a tree, it gets converted into only 4 nodes. So it is a simple case. We have to simply put the required pointer to null. Next case is we are trying to remove a node which is having single child. Either the left child or the right child is present. So again, it is a simple case. In this binary search tree, we are trying to delete 1, 8, 18. And 18 is a node which is having only single right child. In order to delete this node, what we have to do? We have to simply connect this 5 to this 18. That means we have to create this linking. So what we have to do? Right of 5 should be set to 21, and if we are maintaining a parent pointer, then parent of 21 has to be set to 5. And once we have created this linking, we can now delete the node by releasing the memory occupied by this node. So after the deletion, the structure of a tree gets converted to like this. So again, this deletion case is simple. Next, in order to delete a node having two children, then we have to make use of in-order successor or in-order predecessor. And the process goes like this. If we have to delete a node having two children, then what we will do? We will first find its in-order successor. After finding the in-order successor, we will copy the contents of the successor to the node which is required to be deleted from the binary search tree, and then we will actually delete the node that is the in order successor of the node. That means the node which is actually getting deleted from the binary search tree is the successor node of the actual node. So we all know what actually the successor means. Successor means we have to traverse the right subtree of a node for the minimum value. Minimum value, that means we have to traverse the left pointer till it becomes null. So the moment I say we have to traverse the subtree till left pointer becomes null, that means we are actually converting the case of a deletion of a node with two children into a node with one right child or a leaf node, because the minimum in the right subtree should be a node with 0 left child. So if the left child is not present, that means either the right child is present or not. If the right child is not present, that means the node is a leaf node. Otherwise, if it is present, then we have actually converted the case into the previous case. That means deletion of a node with single child. And we can work either with the predecessor or with the successor when we are trying to delete a node with two children. So if we talk about predecessor, that means we have to make use of left subtree. And in the left subtree, we have to traverse the subtree for the maximum node. And then we will copy the contents of the predecessor to the node. And then from the left subtree, we have to delete the predecessor. And if I talk about the maximum in the left subtree, that means the predecessor. That means we are traversing the tree till right pointer becomes null. That means we are actually converting the case into the leaf node deletion, or we are trying to delete a node with single left child. So these are the three cases which we have to study for the deletion in binary search tree. So looking at the example for the node deletion with two children. So let's say this is the binary search tree. We are trying to delete 1 to 12. So it is a node with two children. So I can either work with the predecessor or with the successor. So if I work with the successor. Then we will pick the right subtree of 12 and then find the minimum. So in this case, minimum comes out to be 19. So after finding the successor, what we have to do, we have to copy this 19 to 12. So we will get a structure something like this. 19 is appearing 2 times in this binary search tree. After copying the contents, what we have to do, we have to perform the actual deletion in this subpart of the tree. Then we will delete 19 from this subtree. So after the deletion of 19, since it is a leaf node, we have to simply set the left pointer of 21 to none. So we will get a tree something like this, which is a binary search tree. So as I said, we can either work with the successor or with the predecessor. If I work with the predecessor, in that case, what will happen? This 9 will be used to replace 12. So for that, let's have a look here. So this is a visualization link. We have created the same tree here. We are trying to delete 12, and this platform, it makes use of the predecessor concept. So definitely 19 will be found and then it will be used to replace 12. So let's type 12 here, which we wish to delete. So first we have to search for 12. If 12 is found, then we will check if it is a two-child node or not. Since it is a two-child node, so we have found the predecessor, copy its value to it, and then finally we have deleted the predecessor. So this tree is also a valid binary search tree. So while deletion of a node having two children, we can either work with the predecessor or with the successor. So now we will have one more example. We will quickly revise all the three cases and then we will go at the implementation part. So let's try to delete 3 first. So deletion of 3, that means it is a leaf node. We have to simply put left of 5 to none. So we will delete 3 from this structure. First we have to search for 3. So we have to follow the simple steps of the searching. Once 3 is found, accordingly the parent pointer of 3 should be set to none. So this is the resultant structure after the deletion of 3. Next we will try to delete 9. So 9, it is a node with single right child. So basically what will happen, we will search for 9 and then 7 will be linked to 11. And then we have to release the memory pointed by the pointer of node 9. So we have searched 9 and then we have to remove it by connecting 7 and 11 directly. So this is the deletion of a single child node. And then we will try to delete 1717. It is a node with two children. So since this platform, it makes use of predecessor concept. Predecessor, that means we have to traverse the left subtree of 17 for the maximum value. Maximum comes out to be 16. So this 16 should be used to replace 17 and then right of 15 should be set to null. So let's see what is happening here now. So we are first searching for 17. 17 is found. Then we are traversing the left subtree for the maximum. 16 is used to replace 17 and then 16 is finally deleted. If we have to work with the successor, then we can have something like this. So again, this is the same tree and we are trying to delete 17. So before we have used the predecessor, now we are going to make use of successor. Successor, that means we have to traverse the right subtree of 17 for the minimum. So minimum comes out to be 19. So after finding 19, what we have to do, we will replace the 17 with 19. Okay. And then we have to delete 19 from this tree. Since 19 single child node, we have to create a link between 19 and 21 and then we will delete this node actually. So after the deletion, the tree will get converted to something like this. We have 17 removed, 19 is connected to 21 directly now. So this is all about the concept related to deletion in binary search tree. Next we have to switch to the implementation part. So deletion in binary search tree, that means we have to simply update the required pointers. That's it. Nothing else has to be done. Again, we are going to discuss two implementation here also. One, We assume that parent pointer is maintained in each and every node of a binary search tree, and in another we will assume that parent pointer is not maintained in the nodes of a binary search tree. The main purpose of the discussion would be to make you understand about all the required pointer updates while deleting a node in a binary search tree, because once all the pointer updates are clear, implementation would be easier. So starting with the implementation now. So this is the procedure with the help of which we are going to implement the deletion. So it is simply implementing all the three cases. We are checking if left is nil or not. If left is equals to null, that means it is a case of single child. Then we are checking if left is not equals to null, then right is equals to null or not. Because if right is equals to null, that means it is again a case of single child. And if line number 1 and line number 3, they both give us false, that means it is a case of two child. So instead of discussing the code, we will start directly with the example. Let's say this is the tree and we are trying to delete one from this tree. So what we will do, we will call a delete procedure. It is accepting the tree T and the node to be deleted, that is Z. We have to first check if left of Z is null or not. So we have assumed that we have already performed the search procedure in the binary search tree and the node found is identified using a pointer Z. So we are checking if left of node is null or not. In this case, left is equals to null. In fact, it is a leaf node. So this line number 1, it is actually handling both the cases, that is a leaf node case as well as a case in which right child is present but left child is not present. We will discuss both the examples here. Again, left is null, so it will call a procedure transplant t z comma z dot right. So transplant is a simple procedure, and what it is doing, it is replacing the node u in the binary search tree with a new node v. And by replacement, that means it is updating a few pointers only, not all the pointers. It is updating the parent pointer of v as well as it is also updating the left or right child pointer of the parent of u. So parent of v will be set to parent of u and u must be the right child or the left child of its parent. Accordingly, v will become the left or right child of its parent. This is the only thing which we are doing with the help of this procedure. We are not working with the left or right pointer of the v. The left and right pointer updates of the node v has to be handled by the calling function, which in this case is the delete procedure. So if we look at the transplant procedure, then what it is doing, it is simply checking if parent of u is null or not. So what our motive is, we have to replace u with v. So if parent of u is null, that means u is the root of a tree. So now new root of a tree would be v. If parent is not null, that means u must be the left or right child of its parent. So if the parent is not null, we will check at line number 3 if u is the left child of its parent or not. If it is the left child, then new left child will be v. If it is not the left child, then it should be the right child. So new right child should be v. And if v is not equals to null, then we have to update the parent of v also to parent of u. Since left of z is null, so this transplant procedure will be called, and now we have called this procedure for z comma z dot right. So z, that means one node is identified with a variable u, and z dot right is nothing but null. So when this process gets executed, we will check if parent of u is null or not. So in this case, parent of u is 2, it is not null. So line number 1 will give us false. Then u is equals to u dot p dot left. This is u dot p will give us node 2, and u dot p dot left, that means we are talking about this pointer. So this pointer is actually pointing to node u. So line number 3 will give us true. So the new child of left will be v. So new child of left pointer of 2 will be v, that is null. So basically once this process completes, this left of 2 should become null. And then line number 6 will be executed. We will check if V is null or not. Since in this case V is null, that means V node is not existing. If a node is not existing, we cannot update its pointer. So after the execution of this procedure, what will happen? Only this left of 2 will point to null. That's it. So this is something happened after the execution of transplant procedure. So once we have set this pointer to null, we are free to release the memory occupied by this node 1. So we will then release the memory, and finally the structure of a binary search tree is something like this. Next we will try to delete this 2. So as I said earlier, this line number 1, it is handling both the cases, that is a leaf node case as well as a case of a node in which left pointer is null but right is existing. So we have just deleted the leaf node. Now we will try to delete this node 2 whose left pointer is null but right is existing. So we will call this procedure. Now the pointer Z is pointing to a node 2 which is to be deleted. So since its left is null, again transplant procedure will be called with Z comma Z dot right. So U is equals to Z but Z dot right is 3. So V is actually this node. So this is U and this is V. Again parent of U is not null. So we will check if U is the left child of its parent or not. So again U is the left child of its parent. So we have to update the left child of the parent to V. So basically this pointer 5 left, it is pointing to this 2. It will start pointing to this node 3. Similarly, we will check if V is null or not. So in this case, V is actually pointing to a node. We have to update the parent of this 3 also. So it is right now pointing to 2. After the execution of this process, 3 will start pointing to 5. So once we complete the execution of this transplant procedure, what will happen? This 5 and 3, they are linked to each other directly, and this node Z is free now and we can remove it from the binary search tree. So after the deletion, we have a tree with only 3 nodes. This. Next, if we have to delete a node with only left child and null right child. So in this case, line number 1 will give us false because left is existing, left is not equals to null. So we will reach line number 3. We will check if z dot right is equals to null or not. So in this case, z dot right is null because we are trying to delete 10. So what will happen? We will call the transplant procedure with z comma z dot left. Z will become u and z dot left will become v. So after the execution, what will happen? We will first check parent of u is null or not. So in this case, parent of u is null. We are actually updating the root of a tree to v. Since this if is executed, rest all the else ifs, they will be discarded and we will reach at line number 6. Then we have to check if v is null or not. Since v is not equals to null, so parent of v will be set to parent of u. So parent of u is null. So this pointer will be set to null in addition to the setting of root to this node 5 as well. So after the execution of this procedure, the structure of a node gets converted to like this, and now we can release the memory of this Z node. So after the deletion, the binary search tree, it will have only single node, that is 5. So this is all about the simple cases. Next we have to look at the two child case. So two child case, there can be two things. So we are going to discuss two examples for this condition. So let's say this is the tree and we are trying to delete node 12. So what will happen? Line number 1 will give us false. Line number 3 will also give us false. So line number 5, we have to find the minimum in the z dot right and point that node with y. So when tree minimum procedure gets executed in the right subtree of 12, y will point to this node 19. So we have something like this. Now we will check if y dot p is not equals to z. That means parent of y is equals to z or not. So in this case, parent of y is not equals to z. So this if at line number 6 is giving us true. So what we have to do, we have to call transplant procedure for y comma y dot right. That means in place of y, we have to put y dot right, because this y will be used to replace z. So we have, our motive is we have to first disconnect this node 19 from this subtree. So that's why we are calling y comma y dot right. So now u is pointing to 19 and v is pointing to 20. After the execution of this process, what will happen? 21 and 20 gets linked to each other directly. So this will be the structure. 21 and 20, they are connected to each other. After this transplant, what will happen? Y dot right equals to z dot right. That means right pointer of 19, it will start pointing to 21, and y dot right dot parent will point to y. That means y dot right is 21 now. Parent of 21 is right now 12. After the execution of line number 9, parent of 21 will be y only, that is node 19. So after the execution of lines 8 and 9, the structure gets changed to something like this. Now right of y, it is pointing to 21, and parent of 21, it is pointing to 19. Next, what we have to do, we have called transplant procedure for z comma y. That means we have to replace z with y. Replacing z with y, that means parent of z, that is 5, it will get connected to node 5 by the execution of these steps. Because what will happen, we will check if parent of u is null or not. So parent of 12 is not null. So we will check if parent and child, they are related to left child pointer or not. They are not connected via left child pointer. Instead, they are connected via right child pointer. 5 and 12, they are connected via right child pointer. So line number 5 will be executed. So right of 5 will be start pointing to y. And then we will check v is not equals to null. Node 19 is not equals to null. So its parent will start pointing to node 5. So after the execution of transplant procedure at line number 10, the structure of a binary search tree gets converted to something like this. These are the pointer links right now. And after that, what we have to do? We have to simply disconnect the left subtree of z and connect it to the left of y. This is the only thing required to be done in order to release this memory pointed by node z. So what we will do? Y dot left equals to z dot left. That means 19 left will start pointing to 9, and we have to update the parent of 9 to 19, that is y dot left dot p equals to y. So after the execution of line number 11 and 12, the structure is something like this. So you can observe that the node z, it is now not connected to any of the other nodes. It can be released. So finally, when we release the memory, the structure gets converted to something like this. So we have actually tried to delete 12. 12 is a two child case. So 12, it will be replaced with 19. So we have 19 over here. 21 is the right of 19. And after the deletion of 19, 20 will become left of 20. So this is the final structure after the deletion of node 12. So here, what is the case? We have replaced 12 with 19, which is the in-order successor of 12, and 19 is not the right child of 12. But in some cases, we will find the successor as a right child of the node to be deleted. For example, if we try to delete 10 from this binary search tree, then we will look at the successor, and successor comes out to be the node 15 only. So if successor is the immediate child of the node to be deleted, then in that case there is no need to update the right child of the successor node, because it will remain same even after the deletion. So what only thing we have to do, we have to simply disconnect this left subtree of the node to be deleted to the left subtree of this y. So that's why we are checking at line number 6. What we have to do, we have to simply update the left pointer of y, because the right pointer of y will remain same even after the deletion if parent of y is equals to z. So in this case, it is a two child case. So again, line number 1 and line number 3 will give us false. So line number 5, we have computed the y and y comes out to be 15 here. And then we will check if parent of y is z or not. So since parent of y is z, line number 6 will give us false. So we will directly call the procedure transplant t z comma y. So z is equals to u and y is equals to v. So after the execution of this transplant procedure on z and y, what will happen? This 20 and 15, they will get linked to each other directly. So this is the structure after the execution of this transplant procedure at line number 10. Then what we have to do, y dot left equals to z dot left, y dot left equals to z dot left, and parent of 5 will start pointing to 15 by means of line number 12. So we have this structure now. So now I can release the memory pointed by 10. That's it. So this is the tree. We were trying to delete 10. After the deletion, what will happen? 15 and 18, they will be used to replace this subtree as the root. So we will get this structure. So this is all about the deletion in binary search tree using an iterative procedure and assuming that the parent pointer is maintained in each and every node. So if parent pointer is not maintained, there is no need to update the parent pointer. But if it is there, then it has to be updated properly. Otherwise, the structure of a binary search tree will affected by it, and it may create the problem in the implementation of other procedures. So next, the procedure which we are going to discuss is the deletion again, but now here we are going to make use of recursion, and also we are assuming that the parent pointer is not maintained in a binary search tree. So the procedure name is tree delete without parent, and it is accepting a root and the key value to be deleted. It is not the node, it is actually the key value. And if you observe line number 2 to line number 7, then we are not doing anything, but we are simply performing a search for the key k in the binary search tree. So again we have to check if a binary search tree is existing or not. So for that we are simply checking if root is null or not, because if root is null, there is no need to perform any search. Otherwise, if the tree is existing, we will check if the key value is less than the node value or not. If it is less than the node value, that means we have to traverse the left subtree. And it may be the case that x dot left, that means the node which is the left child of x, may be its value is equals to k. So we are actually trying to delete the left pointer of the x itself. Therefore, if we are trying to delete that pointer, we are actually updating the left pointer of x also. Therefore, we are calling this procedure again for x dot left comma k, and whatever this procedure is going to return, that value will be used to update the x dot left pointer. Similarly, if we are moving towards right, then it may be the case that we are trying to delete root of the right subtree of a node. So accordingly, x dot right will be updated, and therefore we are calling this procedure with x dot right comma k, and whatever value this function will return, that will be used to update the right pointer of x. And if line number 4 and line number 6, they both gives us false, that means we have reached a node x whose value is equals to k. So once we have reached the node, we have to simply look for the three cases. So here we are checking if left is null or not. If left is null, then we have to return the right child of x. Similarly, if right is null, we have to return the left child. And if right is not equals to null, left is not equals to null, that means it is a case to delete the node with two children. So we have to first compute the successor. That means we have to call the tree minimum procedure on x dot right. And then we are simply replacing the key value at x with the key value of temp. And then what we are doing, since we are working with the successor, that means right subtree. So whatever deletion will happen, it will happen at the right subtree of x. It may update the right pointer. So accordingly, we have to call this process again with x dot right, and now key to be deleted is the successor value, that is temp dot key, and the return value of this function will be used to update the x dot right pointer. And then lastly, we have to return the node x in order to maintain the proper pointers in the binary search tree, which is similar to the case of insertion. So we are going to look at few of the examples now. So let's say from this subtree we are trying to delete one. So first call to this procedure will be, we will call this function with root comma 1. So during the first call of the function, x will point to the root node 5. Now since we are searching for 1, so line number 4 will give us true. So x dot left will be updated with the function call to the procedure with x dot left comma k. So the second function call will be at node 2. Now x will point to this node 2. Since 2 is not equals to 1, so again a procedure will be called for this node which is equals to 1. Now x is pointing to this node. The moment we call procedure for this node, that means the third call of the procedure, line number 2, line number 4 as well as line number 6, they all return the false. So else will be executed. Here we will check if left is existing or not. But here left is equals to null. So what we will do, we will execute temp equals to x dot right. So temp is nothing but this null pointer. Now we will delete this node and return this temp. So if you have observed, we have called this procedure for left of 2. That means this line number 5. So this return temp, it will be used to update the left of 2 with the null pointer. So the moment this third recursive call of the function gets completed, this structure of the tree gets converted to this. Whatever temp we have returned, that is used to initialize the left of 2. Now we have executed x dot left equals to procedure call. Now nothing else will not be executed, so we have to return x. Now this return x will be used to update the left pointer of 5. So now this pointer will remain as it is even after the execution. So now the second procedure call for the function gets completed and we have reached at the first call of the function. So now it will again return x because we have already executed line number 5. So rest all the other lines, they will not be executed. So at the end we will again return x, which in this case is the same root itself. So this will give us the final tree, and with this we have completed the deletion of 1. So next we will try to delete 2. So again first process call, x will point to the root node. Now since we are trying to delete 2, so line number 5 will be executed. We will call this process for 5 left. So after that second recursive call, we have reached the node which is required to be deleted. Again else will be executed at line number 8. Left of x is null, so temp equals to x dot right. That means in this case temp will point to this node. We will delete x, so that this node will be deleted and this node will be returned, and now it is used to update the left pointer of 5. So after the execution of the second recursive call of the function, the structure of a binary search tree, it gets modified. And now again we will return the root from this function. So with this we have completed the execution of the deletion of 2. And now we will see if we have to delete a node 5. Okay, so it is a node which is having 2 children. So line number 2 false, line number 4 5 is less than 5 no, 5 is greater than 5 no. So line number 8 will be executed if at line number 9, and else if at line number 13 it will give us false. So line number 17 will be executed. So in this case temp is equals to tree minimum x dot right. That means temp will actually point to this node. Then what we have to do, we have to update the value of x with value of temp. So in place of 5 we have to put 18, and then we have to call the delete procedure on x dot right. So we will call the delete procedure to update this pointer of the tree, and from this tree we have to delete 18. So after the deletion of 18 it will be replaced with null only. So here we are trying to delete 5, and after the execution the tree will get updated to something like this. So here all the cases of nodes having 2 children, they are handled with the help of these 3 lines. But previously we have handled this case in two different ways. So both the ways are possible. Just try to update the pointers as per your convenience, but you have to update all the pointers properly. If you're maintaining a parent pointer, update it properly. If you're not maintaining it, then you have to update the pointers accordingly. So we have discussed both the ways. Just try to get the update concept of all the pointers while deleting a node in a binary search tree, and then you have to start with the implementation. So that's it for today. Thank you.